Hello everyone, and welcome to this video number 6, where we have we're going to continue on electromagnetism. This video we're going to start with the question number 26. Two identical metal spheres with charges plus 3q and minus q respectively exerts a force F on each other with separated when separated by a distance r. So when they are brought into contact, separated, and returned to their original position, the mutual force becomes which one of these four? We have a similar question of the one we have seen previously. It was the r which is changed, but now the q's will change in this case. So let's get back to the famous formula. F equals q1 q2 over r squared. So for our case here, F gonna be the k, the q1 is plus q or plus 3q. Let's take the absolute value because the magnitude is what matter here, times the minus q divided by r squared. That's giving the k 3q squared divided by r squared. So this is for the first state. For the final state, we say that the two charges brought to contact and separated again with the same distance. So we need to know what happens once they are touching each other. So we know that the spheres are identical. That means once they brought to contact, they will share equally the total charge. So the plus q or plus 3q, here we have plus 3q minus q, that's giving the plus 2q. This is the total charge of the both of them when they are brought to contact, when they are touching each other. So this is 2q. Once they are touching each other, they will just like distribute the total charge equally. This is important. That means once they are again separated, each one will take the half of the total charge. So we have the total charge here is 2q. That means the first one will take plus q, the second one will take the plus q. So this is the charge of each after they have been in contact and separated a second time. So let's have a look at the formula. What's gonna give in this case? It's gonna give the q times q divided by r squared. This is giving a k q squared divided by r squared. So to get the same expression here, we can just like divide by 3 and multiply by 3. In this case, we have in this expression, which is exactly the expression of the previous f. That means the f prime would be 1 over 3 the f. So the new f would be 1 part over 3 of the original f. That means the A is the correct one here. So I hope you understand or you did understand this event here, what happens exactly for the charges for identical metal spheres. All right, so for the 27, what do we have here? In the circuit shown with the electromotive force E and internal resistance R as the slider of variable resistor R moves downward, the radian of the voltmeter and the ammeter A will change to one of those. The description of the scheme here, we have we can draw that as like this. This is the battery, and its internal resistance small r. This is the selector, and this is the capital R that's going to change. So here we have the ammeter that's measuring the current, and the voltmeter that's going to measure the difference of potential or terminal potential of the battery. Okay, so the R here, the selector is moving down. That means the story here is to understand what happens once the selector is moving down. So here, as the selector is moving down, that means the R, or the resistance of the capital R, is decreasing. Okay, let's get back, or let's state what the Ohm's law says. We do know that the Ohm's law says that the potential is the resistance times the intensity. For this circuit, we have two R's. We have the small r and the capital R. That means the V, or in our case here, this is the electromotive force. The E would be the R plus R all multiplied by I. So the I would be the electromotive force divided by the total resistance of the circuit. As the selector is moving down, the R decreases. So mathematically we have here the capital R is in the denominator. If it's decreasing, that means the ratio will be increasing, which means the I will increase here. So the intensity of the current will increase as the selector here, or the variable resistor, moves downward. So we can just like choose between the A decreases or the D decreases, one of these two. So to know which one is the correct one, we need to determine what happens for the V. So we say here the V is just like reading of a voltmeter, and this is the V here. And for sure the V is the potential, or the potential in the terminals of the battery. Okay, so what is measured here, actually let's denote it as U. The U would be equal to the electromotive force minus the drop of the tension here, minus Ri. Okay, so we say previously that the I is increasing, but once we subtract something that's increasing, that means the U decreases. So the U will decrease, or the V will decrease. That means finally the D is the correct one here. Let's move to the 28. So for the 28, we have here, which of the following statements about magnetic flux line is false? That means the incorrect one. 3 among these 4 are correct, but 1 is incorrect. So magnetic field lines are closed curves. That is correct, because we have something like that. They are closed. Even we can do that. For the B, we have the density of magnetic field line indicates the strength of the magnetic field. This is also correct, as the lines are packed together, as the magnetic field is strong at that point, exactly like at the poles here. Like for here and here, they were the strongest, I mean, magnetic field. So magnetic field lines can intersect. This is the incorrect one actually. If we get back to the schema here, this image shows that there is no any line that's crossing another. Each one has its specific path but not intersecting. We cannot find something like that. If we have a certain line like that, we cannot find another one just like having something like that. So this is not happening actually. For the magnetic field line outside the magnetic extend from the North Pole to the South Pole. That's what happens actually. It getting out of the north, the arrows are directed to the south one. Getting out from the N and getting in the South Pole. So we're going to choose the C here. For the 29, a series wire carrying a current is perpendicular to the paper. If the current flows outward, the direction of the magnetic field at the point around the wire is. So to answer this question, we're gonna need to apply what we call the right hand rule. What happens if a certain current is flowing through a wire? It's generating what we call a concentric magnetic field, where the wire is the center. So here the right hand rule says if we point in our thumb toward the direction of the current, so the rest of the fingers will indicate the direction of the magnetic field. So this arrow is drawn randomly, but it must be something like that, just like the others. So we have a look from the top. This is our eyes, where we see the whole system, and if we look from the top, we're going to see just like the direction of the magnetic field are concentric circles pointing counterclockwise. With that being said, we can say that we have here for A pointing to the wire along the radius. That is not correct. We can never see something like that. This is the line or the magnetic field line. This is not correct. Neither in toward the wire or outward from the wire. So the A is not the one. Wire deviation along the radius, it's not deviating, no. The tangent direction of the concentric circles with wire as the center is clockwise. All of that is correct, but it's not in the clockwise direction. But it is the tangent direction of concentric circles with the wire as the center is counterclockwise. That means the opposite of the clockwise direction. Okay. So for our situation here, the D must be chosen. For the 30, the last question for this video, we have which of the following statements is true about the capacitor? Okay, let's see A, B, C, and D. We have here the capacitance of a capacitor is proportional to the amount of charge it carries. That means if the capacitor is something like that, its capacitance is changing with the amount of charge that it carries. Actually, this is not correct. We can think of a capacitor just like a certain bottle. If we have a bottle like that, with a certain capacity, that means how much of the quantity of the matter can carry if we just like put something inside of it. So it doesn't matter how much we put inside of it, but the capacitance of it is something that is special for it. If we get back or if we get to the relation that's changing or that's expressing the capacitance in terms of the geometry of the two plates capacitor, we have here the capacitance is a certain epsilon times the A divided by D. So the A is the surface or the area, the D is the distance between the two plates. That means the C is proportional to the surface of the plate and inversely proportional to the distance between the two. So this relation will answer our question here. Where is it? Where it is proportional to the area, and where it is inversely proportional to the distance between the two plates. So that's proposition would be chosen. We see for A it's not the one. For B, the more charge a capacitor carries, the greater its capacity. Again, it doesn't matter what are the charges that carries, but the capacitance of a parallel plate capacitor is directly proportional to the area of the facing plate and inversely proportional to the distance between them, exactly as we say. The C is a certain epsilon times the A divided by the D. So the C is our answer here. During the discharge process of a capacitor, the capacitance decreases. The capacitance, it's neither increases or decreases in function of the charge or the discharge of this capacitor. Okay, so the D is not the answer here. In the next video, we're going to start with 31. In a uniform magnetic field, a particle with charge q is injected perpendicularly into the field with velocity v. If the magnetic field strength is b, the magnitude of Lorentz force acting on the particle is. Which one of these four is correct? I will let you the chance to think about it, and we'll answer it all together in the next video. So this is it for today. Don't forget to subscribe and like the video and hit the bell. The subscription button is somewhere here. You can just click on it and join our channel. See you in the next video.